Thank you. Hi everybody, my name is Addison Snell. I'm with Intersect 360 Research. We're industry analysts who cover the high-performance computing market, including topics across high-performance data centers, hyperscale, big data, AI, cloud are all part of our purview. I'd like to get a quick sense of the audience because I looked and I saw there were no prerequisites, so this could really be open to a lot of people. And this, I'm not like doing a survey here or anything. How many are undergrads? Any undergrads? How many grad students? And then faculty or press, politicians? Thanks, appreciate it, awesome. And a sense of, are you in engineering, different engineering disciplines, like software engineering, software engineers, like hardware engineers or EE, other types of engineers, other sciences that aren't engineers, just liberal arts? Very few. Okay, I am not an engineer, so I'm well outnumbered, although Steve might attest I do a fairly good job of impersonating one. I've been in the high-performance computing or supercomputing market throughout my career. I'm an industry analyst. That means we do the kinds of things that you might associate with a larger company like Gartner or IDC. We do market sizing, forecasting, segmentation, trend analysis. We write lots of white papers. We do strategy consulting with companies in this space, try to predict the future, that kind of stuff. I have a weekly podcast called This Week in HPC, which you can find on our website or on iTunes or SoundCloud. We also co-distribute with our publishing partners, HPC Wire, which is the leading trade publication online in this space. So I'm a frequent talker in this space. I've gone with a bit of a high-level overview because I know that you've been talking to some of my colleagues over the past few weeks and they're already heavy hitters, and I'm not going up against Horst or Rupak in terms of what they're going to talk about in supercomputing at the national lab level or in space science and the like. I think they've done an excellent job showing you what can be done with supercomputing at a high level, and I don't need to try to be redundant to that. However, I do have a theme for this talk, which is welcome to the new supercomputing again, which is to say there's certainly a lot of new things going on in supercomputing, and with trends in hyperscale and artificial intelligence, analytics, there's a lot of revitalization of what's going on across the high-performance computing landscape, and that is definitely true. What's also true is that the entire time I've been in this industry, about every 3 or 4 years, the entire industry is going through some major revitalization of some sort. And what happens in supercomputing is we see that constant rebirth of new capabilities coming into the market. So in one sense, things do change, but in another sense, they stay the same. Now, in light of me not being an engineer, and I'll give a quick bio, I actually have an MBA from Northwestern. Then I got started in high-performance computing. I went to Silicon Graphics after Northwestern, where I was in product marketing and product management, starting at, during the big dot-com boom. And I was product marketing for the Origin and Altix line of supercomputers and servers. And that got me into high tech. I became an analyst after that, starting with IDC, and then moved over to this company, which started as Tabor Research. It was originally a division inside Tabor Communications, which is the publishing and events company behind HPC Wire and some other titles and events. But we've been independent now for 10 years. So if you have questions about A, being an industry analyst for your career, because I'll tell you what, I did not, even in college, I didn't say, you know what I want to go do is be an industry analyst for supercomputers. That was not like on the plan. Nor was starting my own company on my own plan, and I can talk about either of those two things, either in Q&A or afterwards, but I thought I'd focus my topic today on the industry at hand rather than my own career path. Now, nevertheless, I'll start with something from the humanities about the new supercomputing again. Can anyone translate this for me, sing out what it means? The king is dead. Long live the king, right? Which, according to Wikipedia, which even industry analysts use, started in the 1400s with the ascension of Charles VII after Charles VI. The whole idea is that we pass the crown on to the successor immediately upon the death of the previous king, which the English loved that idea and immediately adopted it. The king is dead, long live the king, because there can't be any kind of interregnum where there's not a crown, because then that would encourage people to revolt. They would feel like there's no king, and this will guarantee there would never be any kind of civil war or unrest. The king is dead, long live the king. And that's what I'm getting at with regard to welcome to the new supercomputing. Again, yes, things will change, but we believe in high-performance computing and supercomputing as a long-term market, regardless of what disruptive technologies there are in this space. Another quote that I'll throw out there that is often attributed to Mark Twain, but who knows, history doesn't actually repeat itself, but it does often rhyme. I think this is what we find in our career as industry analysts as we look at some of these trends coming through the industry. Here we look at some of the eras in supercomputing, which have been, goes back to even before. In the 1940s, we had computers, and they were supercomputers by default. They were the only computers we had. Here I pick up the thread starting in the 60s and 70s, and some of the iconic computers and also world leaders at different times, and the different processing eras that we've been through. Now, these weird words here you've probably encountered in my predecessors' presentations going through this, but flops, this floating point operations per second, is a pretty standard metric of supercomputing performance. A floating point operation, a floating point is a fancy computer science word for a decimal point, right? It's just not a decimal point because we're often not in decimals, right? So you follow me. But this is millions, billions, trillions, quadrillions, and quintillions of floating point operations every second, and roughly when we've been in those different eras. I didn't draw exact markers, but this Cray 1, which is an iconic supercomputer of its time that debuted in 1976, was capable of 160 megaflops. It wasn't until the Cray 2 a few years later that we broke the gigaflops barrier into the 1980s. Before the Cray 1, we really just had different custom things that governments would build. The ENIAC and the big baby machine at Manchester and the like. The vector era kind of came through with Cray, building on work that Seymour Cray had done at CDC. Vectors are processors that execute strings of instructions all together. If you tell my wife, go to the store, she does that in one command. If you tell me, go to the store, you have to be a lot more scalar about what all of the instructions are for everything that I have to do. It's one instruction versus many instructions. And vectors are very efficient still today for things that have a lot of loops that you can then roll into vector instructions. After that was an era based on what are called RISC processors and symmetric multiprocessing architectures. The Origin 2000 I put up there because it's near and dear to me, and because it built some of the largest shared memory, like single memory space under one operating system kernel in that time frame in the 1990s. These tended to run different varieties of Unix, whether it was IRIX from SGI or HPUX or Solaris, or all the different big Unix companies had their own different flavors of Unix. We also had things like massive parallel processors, which were a special type of clusters that were very thin. The IBM Blue Gene is a perfect example of those, and also a rare example of a code name that became so popular it wound up getting used as a brand name. IBM doesn't typically name its products clever things like that, but Blue Gene, which was supposed to be a one-off for genomics, was so cool at the time and other people wanted to buy it, they wound up accidentally doing 2, 3, 5, a couple dozen or so before the Blue Gene finally petered out. A big revolution that happened here with clusters, the early clusters in the late 1990s were out of something called the Beowulf Project, another humanities reference. A Beowulf cluster was just the idea of a standardized vanilla industry standard cluster that it didn't matter where it came from. I can buy a server from Dell or Hewlett-Packard or Acer or build it for myself from parts I bought at Fry's, and I cabled them all together over Ethernet, and I run industry standard Linux, and I parallelize my application to run on anything. The nice idea there was one of portability. Once I went through the relative pain of breaking up my application so that it could run that way, after that it didn't matter whose parts I bought. So I went to a very industry standard notion of parallel computing. MPI to this day, or message passing interface, which was the new thing with clusters and is still the standard, I still tend to think of as team juggling. If you ever watch team juggling, there's a beat where people do things unto themselves. I pass, I toss, and then there's a beat where everyone has to throw, and there's a beat where everyone has to catch. Right? And those have to sync up, or else it starts going very badly very quickly. And that's how parallel programming tends to look. I could be doing a large-scale weather simulation and assign each processor or node a cell of the weather simulation. And there's a beat where I do my own calculation. And then there's a beat where I have to pass to the other neighboring cells information that go into their areas. And there's a beat where I have to receive all of that same information, and then we can all go calculate again. And it does no good to have one cell out racing ahead of the other cells because there's too much data dependency, right? I need to wait and see what information I'm receiving. So in a sense, it's nice and portable, but take note that a big thing that happens here is a lot of the burden of programming and scalability starts shifting from the hardware vendor past the operating system and now to the programmer, right? And if you're in this space now, the scientists de facto have to be, in a sense, aware of the parallel nature of their applications. You could do this with anything. You could do it with a gigantic long division problem and have 100 teammates and find out how to break up the problem so that you're in charge of these digits, and here's how you have to coordinate with the people who are nearby and get it all to work out at the end. It's just not necessarily the most efficient way to do it for all applications. It is cheaper and therefore took over a lot of the industry. Now we're into an era that I label as heterogeneous. It's still clusters. But here what we had was a supercomputer was a relatively self-contained device. We broke that up in clusters. We went standard but disaggregated. So I could buy the components from anywhere. They were standard components, and then I aggregate them in. Now what's happening is the pendulum is swinging back again more towards specialized components, but they're still disaggregated. We're keeping the notion of disaggregated clusters, but losing the notion of portability and everything's the same. Just looking at the processor space, for example, the dominant processors in this space for the last 10 years have been essentially Intel Xeon processors and their predecessors, the Intel server processor line. But we're now also seeing attachments of various types of coprocessors or accelerators, most commonly graphics processors or GPUs from NVIDIA as be the leading provider. I can attach that onto the system. The reason to choose a graphics processor is they're really good at these floating point operations. And if I have particularly math-intensive parts of my application, I can break them off and send them to the accelerator, do them there, and then bring them back. So it's the notion of a coprocessor. Now, coprocessors have been around this whole time, but they never really took off because A, it becomes harder to program. You have to now explicitly say, do this part of the calculation over here, do that, and then bring it back. B, we didn't have accelerators that in the long term maintain the same pace of development that the major microprocessor providers drove. So you take a company like ClearSpeed had a product in the late 90s into the early 2000s that was a really attractive coprocessor, but over the course of 3 generations, they didn't maintain the same pace of development Intel did. So a couple generations in, it was no longer as attractive to move that calculation over to the processor. And then the third thing is you have to be able to get enough of a speed up from the accelerator that it's worth the latency hit that you take sending it away to begin with, because that's not instant. You have to communicate over some kind of channel. There's a transmission time, and then I have to bring things back and reassemble. So I automatically take a penalty for sending something away. It's like if I'm going to send my laundry to China and then bring it back, it's got to be cheaper enough that it's worth not only the price that I spent to send it, but also the time lag to get it back. NVIDIA really led the charge over the last 12 years in addressing all of these things. Because they're driven by the gaming market, they maintain a pace of development that keeps up with Intel. They've been pushing a development environment called CUDA that's a lot more C-like or C-friendly, C++ friendly. So you still have to call a library explicitly, but you can do that more in the construct of the programming you were already doing. And then furthermore, there have been developments along the interconnect channel with new generations of PCI Express, which is now moving on to PCIe 4, but also custom things like NVLink to speed up that transmission so you don't have as much of a latency hit. So that's an example of heterogeneity. It's not the only one. AMD is back into the game. They have their own GPU. IBM is still pushing power processors. That's a different kind of 64-bit processor. We see thin processors that are targeting things like AI and analytics that are also co-processors, like the Nirvana processors that Intel has. There are things called FPGAs, field programmable gate arrays, which is another type of accelerator or co-processor. And then we have ARM processors, which are the thinner, smaller processors that are in these things. We can gang those together theoretically a lot cheaper if we can also do the work in parallel. And we're starting to see ARM-based supercomputers come into the market. Just looking at the processor architectures themselves is already a wider degree of heterogeneity than I can remember seeing in this market in a long time. I'm back here, you had different flavors of Unix and different types of RISC processors, but it was all in the similar envelope. Here, it's kind of wide open. And then you have different types of interconnects or ways to network the processors together, different tiers of storage. There are all kinds of different ways that this is going heterogeneous or specialized, but still disaggregated, which again, amps up the challenge for the programmer and for the administrator in terms of how you build a scalable solution. A couple of the things up top, I put ASCII Red up there. That was Intel was the prime vendor on that. It was the first supercomputer across the teraflops barrier in 1998, 96, something or 90, yeah, something around there. 1998 was the first machine at the teraflops barrier. Interesting because they did it with a cluster for the first time. They narrowly beat out an SGI Origin that was coming out at the same time. And also because Intel was the prime vendor, which is unusual, or that was the only time so far that they were the prime vendor on a large supercomputing bid. They've done it now again for one of the computers coming out in the exascale era that's planned in the 2020s. The Aurora supercomputer at Argonne National Labs is an Intel-fronted contract, but with Cray as the system provider. The Earth simulator is noteworthy not only because it dominated as the most powerful supercomputer. Oh, I even put the year on there, 1996. I gave myself the note and then I forgot what it was. ASCII Red was in 1996. The Earth simulator was the most powerful computer in the world for several years, starting in 2002. Noteworthy not only for its dominance, but this was in Japan with NEC was the vendor, and it was a vector architecture. NEC still does vector architecture computers. And I put that on there because I don't mean to imply that just because something's further to the left on here means that it's dead. You can still find vector architectures today, SMP architectures today, standard Beowulf clusters today, but you have more choice in the market. Tianhe 2 was the most dominant computer in the world for a couple of years. China starting its own development of their own processors, their own interconnects, their own everything, because they want to be less reliant on US developed technologies. And there's a lot of politics involved in this, and still a lot of politics involved in this, because at a national level, national security interests try to dictate, well, we want our supercomputers to be better than their supercomputers. And the US government will even start putting restrictions on what can or can't be sent overseas. there's something called the Top 500 list, which I'm sure you've heard about in a previous session, that does rankings of the most powerful supercomputers in the world, according to the LINPACK benchmark, which is an imperfect and arbitrary, but that's the one that we're going to use, benchmark. So fine, let's use it. Currently, it's a US supercomputer called Summit on the top of the list. A couple weeks ago, it kind of got out. It's supposed to be a secret, but China has a supercomputer that's 40% more powerful than Summit, allegedly. There's not a lot out about it publicly, and China isn't always a free press society. They tried to keep it secret, but nevertheless, it's more or less accepted that China, in fact, has the most powerful supercomputer in the world right now. Although it's not on the list, they're keeping it secret. And that led the US government again to put restrictions on what can and can't be sent to where. So this is, again, a noteworthy supercomputer, and there's a lot of eyes on this as we start looking toward what's going to be the first supercomputer capable of exaflops as we head into the 2020s. Traditional supercomputing has been all about science and engineering. One of the easiest definitions of of what constitutes high-performance computing, in a nutshell, you're looking for computers for scientists and engineers doing science and engineering. That is a nice one-tweet definition that leaves out a couple of things, but is not bad as a starting point. If you go to Toyota buys a lot of computers they use for a lot of different things, but the ones that they use for designing new cars, trucks, and minivans tend to be high-performance computing. And you can extrapolate that to Pfizer and drug discovery, or ExxonMobil and finding new oil reserves, or the CIA and spying on people. Whatever it is that's your core mission of what you do tends to be where you see high-performance computing deployed. We also see that going into new areas like in finance. Finance is one of the largest vertical markets for high-performance computing. Whether that constitutes science or engineering is dependent on your argument of whether economics is a science or not. If it is, fine, it's science. If it's not, well, fine, they're doing it anyway. They're doing an awful lot of high-performance computing in finance. I cribbed all of these images from Barcelona Supercomputer Center's website because I was there giving a presentation earlier this year. By the way, if you ever get a chance to see this, this is a Lenovo-provided system, all Intel technology inside this. It's in a church. It's in a chapel. It's billed as the most beautiful supercomputer center in the world. And yeah, it looks pretty great. In fact, underneath all these red tapestries, there's murals up on top that they really want to take the tapestries down. And they're hopeful that the fact that this center plays a role in both a Jack Ryan novel now and a Dan Brown novel. They're hopeful that they can get either Tom Cruise or what's his name in all the Dan Brown movies now, the famous actor, Tom Hanks, you know, in here and film something, and they'll get to take the tapestries down, and it'll be really awesome. All the different applications that are on there are still on there, but it's not just these, and I want to stress that it's not just at the highest level of supercomputing performance. I like pointing out that there are expanding use cases in commercial high-performance computing that aren't just the biggest national labs and academic labs in the world. Companies doing entry-level and mid-range high-performance computing do product development in all kinds of different ways. Simpson Strong-Tie is a company based not far from here in Pleasanton, California. You can find their products if you go to Home Depot. If you're doing home construction or something like that, Simpson Strong-Tie makes the steel bits that connect bits to other bits, right? If you're looking for brackets and joists and things of that nature, that's what they make. They're a few important things. They're not a huge company, but they are the leaders in their segment, and in particular, they're quality leaders in their segment. When you look across manufacturing, if you want to go look for high-performance computing, start asking the question, who's the quality leader in each segment? And the ones who view themselves as quality leaders are often the ones who are doing this type of investment. So Simpson Strong-Tie, what are they doing? It's really only been within the last 20 years, starting about 15 years ago, they wanted to start doing more simulation for their products in order to maintain quality leadership over their competitors. You have to appreciate that This is the high liability portion of the construction market. If your house falls down, you sue the person who gave you the nails, not anything else, right? So the bits that join the bits to the other bits, they're actually high liability area and they want to hold up. Out of every high performance computing or supercomputing user I have ever met with in my life, this is the only one still that I can think of where the primary material they're modeling is wood. And think about for a second some of the complexity that comes with that. Wood is not as simple as something like steel. It's organic, it gets wet, it warps. Every piece of wood is a little bit different than the last piece of wood. And that's before you even start controlling for this one's pine and that one's oak or whatever, right? And there's, they were calling the Army Corps of Engineers saying, do you have wood models we can start with feeding into our software? The second most common material they have to model is concrete, which also is no picnic, right? It's, it's not homogeneous through the mix. But the payoff they get when they go to run a stress test on something, I watched them do this. They basically build a section of something and then they've got this massive crane that exerts force on it to see whether it's within spec. So they set up the test, they build the thing, they pour the concrete, and the next thing they do is mark their calendars because we're all going to come back in 6 weeks after the concrete cures so we can run the test. That's how long it takes to set up the test because that's what concrete is like, right? Now they can get questions where a contractor will call in and say, all right, I've got this joist in the middle of a building and I want to drill a 2-inch hole in it to run an electrical conduit through. Is that still safe? Well, they don't want to set up the whole test. The contractor's not going to wait for that. But they can load up their software, put a hole in the thing and play around with it. And maybe the answer they go back to is, well, yes, but can you put the hole 2 feet lower? Or can you make it an 1.5 inch hole instead of 2 inches hole? Then we'll sign off on it. Having that kind of feedback for them back to the contractor is actually a huge benefit to their business. That's the kind of thing that gets people using those parts. So that's an example of the kind of thing that they do. This is another one I like, wiper blades. This one I'm not authorized to put the company on, but I talked to the CEO of a small wiper blade company, aftermarket wiper blades. So not original equipment, but you go to the store to buy replacement wiper blades. And again, the quality leader in their segment. And I asked them, have you ever thought of doing simulation of wiper blades? And he said, funny you should bring that up. I just had this conversation with the lead engineer on our new product coming up. He came to me and he said he was worried that the new design was going to have trouble with wind lift, which was a term I had never heard till that exact moment, and you probably haven't heard it until just now, but I kind of got it, right? If I'm driving and the windshield wipers are on and the wind is going to pull them up, that can't be good, right? So what am I going to do? Well, there's a couple things I could do. One is I could do a wind tunnel test. Right now, I don't have a wind tunnel. NASA's not going to let me borrow their wind tunnel. It's really expensive, so cross that off. I can't do that. Second, I could theoretically do a computer simulation, but think about it for a second. I mean, it's just a wiper blade, sure, but that's not an easy simulation. By the time I'm modeling the wind and the ice and the curvature of the glass and the car is moving, yeah, it's doable, but it's not an easy simulation to write. The third thing I can do is make the wiper blade, put it on a car, and drive out on the highway with a clipboard and see what happens, right? And I can't make it rain or snow, but I can look up where it's going to rain or snow, and I can send it to my partner in Melbourne and say, can you do this for me? And he'll do it. I thought, well, geez, option C kind of sounds like it. And he said, no, actually, he convinced me we're going to do option B and do the computer simulation because then in the future we can do that faster. Right? And it was all about maintaining that lead over somebody else with what's ultimately a complicated simulation the first time, but then you get a long-term benefit. Then this is a really fun one. Everyone recognizes these little candies, right? Which were, that was the funny thing like a year ago, and I still get a little bit of mileage out of that joke. Procter & Gamble makes this product. And Procter & Gamble is kind of the poster child for bringing these high-performance computing technologies into consumer products. They had a guy, Tom Lang, who retired not too long ago. And one of the, I miss him dearly. He was full of great stories. I mean, he's alive. I just don't get to talk to him. One of the last things I asked him was there ever a product P&G wanted to come out with for a long time, but until they had modeling and simulation in HPC, they couldn't come out with it. And he had one like that. And it was this. It was Tide Pods. And he said, it wasn't like we only just thought of that. Okay, we've been wanting to come out with this product for 75 years, he said. The idea of having a single-use tablet you can huck in the laundry and do that, right, it was kind of obvious. We always wanted that. Now, their competitors had ones that were the compressed powders. You can picture those. P&G never had one that was a compressed powder. People hated them because they work in the dishwasher where it's hot water, but the laundry's cold often. And if they don't dissolve all the way, then you get the grit in your clothes and everyone hates that, right? What I love about this is everyone can picture it. Even you guys do laundry, right? And so we knew it wanted to be a liquid, fine. P&G has liquid fabric softener. They have liquid detergent. What's the hard thing here to design? It's the envelope. The envelope is really hard to design because what you need here, this little square, has to be a plastic that will dissolve immediately and completely in cold water, but not get dissolved by the liquid inside the envelope, which is already a nifty trick. It has to be shelf stable for a long time at a very wide range of temperatures and humidities, shippable. If you think you've got all that, you have to be able to get this liquid inside that package on an assembly line at about 30 miles an hour. And if you think you've got that, if the thing costs more than about 15 cents a pod to make, forget it. It's laundry. You've priced it out. No one's going to pay it, right? So then you design it, and then you see them in the store, and people are like, this was my idea. I told them they should do this 10 years ago, right? This envelope that we've all seen and used is really hard, right, to do that. But you come up with the macrochemical to make that water-soluble plastic, and now you've got a product that's Tide Pods. You realize how much money they've made selling Tide Pods in 2 years? This is a huge product, and it's a chemistry problem. Now, high-performance computing didn't say, here's your chemical. What they did is the same thing they do on the biosciences side, is a lot of target reduction. For the 10,000 macrochemical ideas you have, you want to do fast fail on 9,900 of them and give your engineers the 100 best ideas to go work with. And that's modeling and simulation there. Okay, I'm an industry analyst, so you get a pie chart. I just wanted to give you a sense of who buys high-performance computing. Now, academic is one big chunk that's 17% of the market. I get that there are a lot of different workloads in academia. That's kind of the point. They tend to be shared resource labs. So factoring this out for chemistry versus weather and climate versus anything else winds up being hard to do. Government tends to divide between national security, military, defense kinds of applications and research science kinds of applications, right? So this is your national security, military, not just US. Lots of countries have militaries, but US does dominate the spending in here. And then versus national research labs, national agencies. National agency is what we call a research lab that has a single focus. So that could be weather and climate like NOAA or ECMWF, or it could be the National Cancer Institute. Something like that would fall into national agencies. Then more than half of the market is these different kinds of commercial workloads I'm talking about. Banking is one of the largest. It's either the largest or second largest, depending upon your appetite for combining automotive and aerospace manufacturing, cars and airplanes, with consumer product manufacturing, Tide Pods and Simpson Strong-Tie. If that's one manufacturing segment, then manufacturing is the biggest. If that's two separate ones, then finance is the biggest. That's just a matter of taste. I separate it here because some of our clients like it that way. Finance does a lot of different things. Trading applications like the Flash Boy stuff, the ultra low latency. The biggest, fastest growing areas in risk management, econometric simulations, that kind of thing. They also do pricing applications, analytics. This is designing cars, trucks, airplanes. Biosciences is widely diverse, from pharmaceutical companies to agricultural engineering. Agricultural engineering is what you call it when you want to stay politically outside of the GMO debate and just acknowledge that that exists and people buy computers for it. That would be under biosciences. Energy is the oil and gas space. Lots of seismic modeling, so using computers to figure out where to go drill. AI is coming into that space now. If I can teach AI to read an MRI, I can teach it to read a seismic map for where the oil might be. You're looking for the ancient underground lake beds and river beds that might have dead dinosaurs in them, right? That's where you're going for oil. Consumer product manufacturing, we just talked about. Retail has lots of analytics in it that drives HPC. Chemical here is not biochemistry, that's down here. Chemical is chemical engineering, which is like the Tide Pods example, but here I mean chemical engineering companies like Dow, DuPont, BASF, 3M. They're now starting to pick up steam, and they have an arrow on them because that's the highest growth rate in our forecast right now, is chemical engineering. Ironically, they're driven there by these guys, right? You look at that Tide Pod example. If I'm at Dow Chemical, I'm thinking, what the heck? Procter & Gamble is inventing plastics now? Why didn't we invent the plastic and sell it to them, right? That's Dow or BAS's business, right? So that's going to start driving that investment there. Media and entertainment is mostly not an HPC application anymore. It's mostly a hyperscale application for things like, YouTube and digital content creation and distribution. That's not HPC. The parts of it that are HPC are still in some of the high-end visual effects will drive high-performance computing. And then electronics is chip design. You use HPC for that. Transportation, more logistics. I see a question in the back. Yeah. Hyperscale. I'm going to get to hyperscale in a second, so pin that and come back to it. In fact, it's right here. Hyperscale we're tracking as a separate market from high-performance computing. Hyperscale is what we call the Googles and Facebooks and Amazons and Apples of the world, right? And if I try to get this into a one-tweet definition, the hyperscale market is when you have an arbitrarily scalable web-facing application infrastructure distinct from general IT investment. Believe it or not, all of those words are carefully chosen. It is literally my job to be pedantic and have definitions like this. Arbitrarily scalable means that there's not like a theoretical maximum. Even at the low end of this, something like Wikipedia, which barely qualifies as a hyperscale application but does, there's not some maximum size of Wikipedia. People could keep adding more detail into Wikipedia ad infinitum. You wouldn't get to a point where you say it's finished, right? It scales along with the internet and people's ability to touch it. And then it's essentially web-facing as long as you include web-like interfaces like apps. And the application infrastructure has to be distinct from your general IT. So I could go into PayPal as a good example and say, all right, here's PayPal. Here's their general IT stuff that does their payroll, their CRM system, their HR database, their in-house email. That's just IT. They've got some finance applications that do HPC, the risk management kinds of things I talked about before. And then they also have a hyperscale kind of infrastructure that touches all of their end users. The biggest hyperscale users, so we track that market separate from HPC. There's certainly HPC that goes on within them, but they're so big and so hard to penetrate. The HPC market overall is about $36 billion in product and services spending. Hyperscale is about 45, but concentrated into the tier 1 companies, which our tier 1 is companies that spend over $1 billion a year on IT. $1 billion with a B dollars per year on IT. There were 11 of them last year that spent over $1 billion on their hyperscale infrastructure. The largest of them last year, Google, became the first to spend over $10 billion in a single year on IT. Now think about a large supercomputer tends to be hundreds of millions of dollars in cost. This is 10 times that every year in the billions of dollars. So if you think about the effect that hyperscale starts to have on the market, it's not just what they're spending. It draws the focus of technology companies who want to sell to them, right? You get companies like Intel or NVIDIA saying, well, they're going to be my primary target market and everything else comes second. Because if I can get one of those companies, they become a market maker. They draw a lot of staffing, right? I mean, they're sucking employees out of other computing areas like crazy. It's cool to go work at Apple. And there's everything that has to do with cloud. Because if I go back to these different eras, one thing I didn't put on this is cloud, which has been a major topic of discussion for the last 15 years, really. And what do we make of high-performance computing in the cloud? Is that something that we're going to do? Furthermore, they engender new applications, and right now, artificial intelligence, which you probably heard about from a few speakers prior to me in this series. AI, again, is not entirely new. AI, in fact, the last time it was really big was the 1990s, and you had the Deep Blue supercomputer beating the world at chess, right? And artificial intelligence was going to be this next huge thing. It really, and it was very popular in the press, and then it kind of faded, and we've all forgot about it for a while, and now it's back with a lot of fervor. But a big thing that happened with it is now the real leaders in AI are a lot of these hyperscale companies. Microsoft, Google, Facebook, Baidu are making huge AI investments and driving a lot of the research here because they have the aggregation of not only a lot of computational power, but more importantly, data. They're sitting on data sources like you've never heard of, right? They've got all of the end user data, they've got all the images, they've got all the web data, they've got data, and that's what's needed to train these neural networks to do artificial intelligence. Now, when I say AI, yeah, it's new, yeah, it's not new, but yeah, it's new, okay? So, why we get excited about it, what it really is to me is a new programming approach. Now, when we talk about high-performance computing and some of the things that we do with it, most of what you see on here are applications that you could call deterministic, which is to say it's a math problem that has an answer, right? You plug in a bunch of variables, you do a bunch of math, and it comes up with an answer. It's a deterministic problem. Some application areas, like in finance, which I had an arrow on here, are more what you could call probabilistic. There are some categories of applications where it doesn't really rate to come up with an exact answer. If I asked you to figure out if you shuffled together 4 decks of cards at random and then fanned them out, what is the probability P that some string of 20 cards will contain at least 16 spades? If you went to try to do that with a pencil, great, go at it. I took some probability and statistics. It's just way too hard. It's way easier to write a very simple very simple computer program to do it about 100 million times and tell you how often it happens and figure you're close enough. It's in high performance computing, that's called a Monte Carlo simulation. And they're very common in finance, also biosciences, some areas. So you have probabilistic applications. What AI gives us, or really I'll use the term machine learning to be more general. What machine learning introduces is a new computational approach that you could call experiential. It's neither deterministic nor probabilistic, it's experiential, and we call it artificial intelligence because it mimics how we learn as people. If I go outside and I see a cat, well, I've never seen this cat before, yet I have a very high degree of certainty that it is a cat and this wealth of information around the concept of cats that I carry from my lifetime of experience around cats. In fact, if I walked outside and saw a fox, that's something I see very rarely, but they're in kids' books. I've been taught about foxes. I see them on TV. I have enough that I go, is that a fox, right? And then, yeah, and I'll ask my friend, did you see a fox? Was that a fox? My probability is a little lower, but I'm still pretty certain it was a fox. If I see an ocelot, it's more like, what's that cat thing that's over there that I'm pretty sure is not a cat, but is kind of like a cat, right? My experience is lower. And that's what we're doing with training this machine learning, is we're trying to give it as much experience as possible. Same thing with driving, right? I've never driven on this road in this neighborhood before, but I know how to drive. I've driven in neighborhoods. Well, how do I extrapolate that to driving in downtown Bangalore, right? I've never done that before. I know how to drive. I know what a car is like. To what extent is the experience same or different, right? Well, it's kind of a tweener, right? It's not nothing, but like I'm kind of panicked about it. And machine learning is like that. Now, I did hear a joke once that a guy from Facebook told. Concerned parent says, well, if all of your friends jumped off a bridge, would you jump off it too? Machine learning says, yes. Right? Well, what is the concerned parent trying to get across with that? You need to be able to think for yourself and not do it just because all your friends do it. Machine learning isn't like that. Machine learning is still a computer program. The thing with AI is you have to stress artificial, not intelligence. It's a computer program. It does what it's programmed to do according to the experience you feed it. It does not think for itself. It is important in the context of high-performance computing, not to the extent that it will replace high-performance computing, but to the extent that it becomes part of this whole triumvirate. And I'll walk through this slide and then we'll be pretty close to the end. So high-performance computing, we as analysts are certain, is a stable long-term market for the simple reason that I don't think we're going to run out of science to do. Not in our 5-year forecast, not in the next 50 years, not in the next 500 years. I suppose it is theoretically possible that sometime in the distant future, the last scientist will be at the last whiteboard with people cheering, writing down the last equation, and then science will be done. But generally, that doesn't happen. Science begets science. And the example I like to give with that is even within my career in the year 2000, I was already at SGI, I was in supercomputing, there was the Human Genome Project. And the Human Genome Project used a very large supercomputing infrastructure to be the first to map the human genome. That's great. You've done it. You've mapped the genome. That sounds like the end of a problem. You've finished. Can we go home? Well, no. You've just invented genomics. Great, now there's work to do. Now there are parts of that that get simpler over time. Certainly now compared to 20 years ago, I can now send in a spit sample and get my genealogy and things around personalized medicine. They'll map my genome and that's great. But at the supercomputing end of things, they work on the next level of complexity, proteomics, structuromics, spliceosomomics, whatever it is. It gets more complicated, and HPC is like that. You can refine the mesh, add degrees of freedom, put more fidelity into your model, make it more complicated. My business partner likes to say you don't design the same bridge twice. Yeah, you finish that bridge, but you go and design a harder bridge. You move on. Rarely it does happen that an application type will precipitate out of the bottom of the market because the application doesn't get more complicated as fast as computing gets more powerful. Rendering is the best example of that from my career. Doing the rendering phase of an animated movie when I was early in my career was a supercomputer job. Then it became like a cluster, a grid, a loosely connected network of PCs. Now it's nothing you would consider high-performance computing. There's still computational power that goes into it, but nothing like supercomputing. The computers got faster or more powerful faster than the application got more complicated. Most applications aren't like that. They have this arbitrary scalability. So HPC will be around because the need for it will be there. Cloud, what do we make of that? Will that subsume HPC? Will we just do it all in the cloud? I don't think so. Right now, about 3.5% of high-performance computing revenue is people doing HPC applications in the cloud versus on-premise systems like here at Stanford. The idea that Stanford would shut down all of their high-performance computing and say, we're just going to use the cloud for this, and we'll pay them to do that on demand and do it whenever we want, and it'll be cheaper and more efficient. Is that where you're going? I don't think so, right? There are a lot of myths around cloud, one of which is that it's always cheaper. It's generally not. Not if you're going to consume all of that resource yourself. If you can consume all of the resource, it's the same as car ownership. If you're going to drive it a certain amount, it becomes cheaper to own the car than to call a cab every time, right? And there's more to that metaphor, but I'll stop there. Still, it is part of the overall ecosystem. When I need a lot of resource for a relatively short amount of time, yeah, then cloud starts making a lot more sense, and it'll be part of the overall infrastructure, is being smart about when to use cloud. Big data and analytics was the huge thing about 5 to 7 years ago, and that became a dominant application type that high-performance computing infrastructures would have to start incorporating, but it was never a separate market. This bugged me, where different analysts, oh man, if you want to compete with me as an analyst, here's a way to make a fast buck and it'll work. What you want to do if you want to be, really make money fast as an analyst, A, describe a market that is huge and fast growing. Put any number you want on it. No one will check. The big data market is a $80 billion market growing at 200% a year. It doesn't matter. No one will ask you, out of that $80 billion, how many big datas is that and how much does each one cost, right? Now, a good analyst will maybe hopefully have a methodology of what's actually being counted. And what we found is that, yes, everyone was doing these analytics workloads, but mostly part of the budgets they already had. There wasn't a separate analytics budget. It came out of the data they already had, the servers they already had, the storage they already had, applications they already had that would add analytics modules in. AI is partially doing the same thing. There are people who have separate standalone AI infrastructures, but they're mostly hyperscale companies. Microsoft has a big AI infrastructure for AI inside the company. It's rare that we see that outside of HPC, where it's really distinct from the HPC infrastructure, except for in finance, which is this other arrow down here. And where it's happening in finance is for applications in pricing. Everything has a price, of course, particularly in finance. Usually that's an interest rate. But that gets done in finance today with something called tranche-based pricing. A tranche is a stratum of risk where people all look about the same. And the reason Steve gets a 4.99% credit card offer in the mail and I get a 5.99% offer for the same credit card is because we're in different risk tranches, right? And then I say, all right, I want the offer, so I call up, and then they do another level of review on me and tell me how much money I can borrow for 5.99%. Forget it. That's not what they want to do. This is going to move entirely away from tranche-based pricing to individualized pricing. If you think you're going to have personalized medicine because of AI, I promise you, you're going to have personalized interest rates first. Why? There's lots of money in it, right? There's tons of money in it, and there's huge investments that finance is making today. But this is the point that AI, yeah, it can be a separate application, but mostly what I look forward to is how it interplays together with HPC, not separate from HPC. I talked about, well, can we teach AI to read the seismic map of where to go drill for oil? Sure, we can do that. But, if we can teach it to play Go, we should also be able to teach it the rules of a game like optimize the airplane wing for less drag, right? What are the rules of that game? Can we teach it that? Not to say you're going to get rid of the HPC and the computational fluid dynamics simulation. You still need that. But for decades in high-performance computing, we've been talking about this concept of engineer in the loop, or simulator in the loop, person in the loop, where the engineer makes changes to the model and all of the HPC gets run on the back end to, on the fly, give me all the structure and weight, noise, vibration, harshness, aerodynamics, etc. The latency was too high on that. It never really took off with all the multi-physics models. But what about AI in the loop, right? If I can get AI to just run with that, try this, try this, try this, try this, just like it beat the Go grandmaster by coming up with strategies that hadn't been thought of before, maybe it will come up with an idea. Again, not to replace the engineer, but the same as I was saying with the macrochemicals and the water-soluble plastic. How about this? Do you want to try this? Use the AI to generate new ideas. I'll give you another example that's maybe a little more technical and geeky, but nevertheless I get excited about it. On data storage, it used to be, people have always talked about tiered storage or information lifecycle management and the like. Usually when they talk about tiered storage, historically what you meant was you had disk, which was the data I'm using now, and I had a big archive of tapes, which was the data I wasn't using right now. There were two tiers. Well, now you've got people moving data in closer to the memory with NVDIMM technology and chips, and then you get SSDs and flash memory and burst buffers, different speeds of disk, and the tape is still there. I might have cloud as a tier. Yeah, there's still tiers, but now it's like 5, 6, 7 tiers of hot, fast storage down to cold, slow storage. We're going to move into an area where high performance storage is not so much about I have a ton of bandwidth to this one tier, but more about getting really smart about when is the data on the hot tier. If I can get the data onto the hot tier before I ask for it, then that becomes high performance really fast. So this is something like a parallel file system to a big disk array. That's like, well, Disneyland has the huge parking lot and they're putting in more monorails to get people there faster. That's nice, that's a good thing. But here what we're talking about is making cascading series of smaller lots in closer and getting predictive about here's somebody coming out of the park, promote their car so it's there when they come out of the park. Now that's a level of AI that you could theoretically build into a storage operating system, in theory, to engender higher performance storage. All right, so I'm going to start wrapping up because there's a lot of different trends here. Welcome to the new supercomputing. New by this week, by the way, Cray has swept the podium in bids for the first 3 United States exascale systems. The Aurora system at Argonne National Labs, the Frontier system at Oak Ridge National Labs, and announced earlier this week the El Capitan system at Lawrence Livermore National Labs will all be Cray architectures. So go back to that Cray 1. Cray is also alive and thriving. They're actually going to be acquired by HPE later this year. This is none of those. This is their supercomputer at the High Performance Computing Center in Stuttgart. HLR is how you say high performance computing in German. Hochleistungsrechenzentrum Stuttgart. So Cray is still alive and well, but we're going into this exascale era. There's a lot going on with artificial intelligence. I would encourage everybody to think about not only how does that apply as a standalone, but how does that apply together with other disciplines. I loved asking about who's in other areas of science. You're going to be a huge part of this coming forward. I asked a guy named Keith Gray, who's one of my favorites at British Petroleum once. I was trying to get a sense of what skills were needed out in the workforce. And I said, if I give you a magic wand and you could tap 2 people in your organization to replicate them, which 2 would you pick? And he said, well, can I pick the same person twice? And he had one person who had a doctorate in geophysics and was an expert in parallel programming. He had 1. And he would like to have 3 of those, right? Because yes, you need to understand how to get these applications to scale, but the domain expertise is also critically important. Whether you're talking about seismology or whether you're talking about chemistry or climate simulation, having somebody who's an expert in the domain at hand as well as passively knowledgeable in how to do parallel computing is now a highly valuable individual. It doesn't just all go to cloud. It doesn't just all go to AI. That's the notion of computing as a fungible commodity, computing by the pound. High performance computing is not about computing by the pound, and it's not going to be, because it's linked directly to competitive advantage, whether it's in discovery in an academic setting or security in a national setting or straightforward competition in a commercial setting, all of which exist. The investment in high performance computing is perpetual and ongoing because I'm trying to beat the next guy, right? And it's a thriving industry and it's exciting, which is why I dedicated my career to it despite not being in engineering. So I love doing these kinds of talks. I love our partnership with the High Performance Computing Advisory Council. I look forward to being back here at Stanford in February as part of that series, and I appreciate you joining me here today. Thank you.